Let us know.
Yes, please proceed, Karen.
Okay, hello, everyone. We're having a little technical difficulty here, but we're managing it. Hi, everyone. I'm Karen McCabe. I'm with the IEEE, which is the Institute of Electrical and Electronics Engineers, and is known as one of the world's largest professional association with 400,000 members in the world in 160 countries. But really to note is our remit of advancing technology for the benefit of humanity and the work that is done under the IEEE platform. And we are here today to speak a little bit about ocean sustainability and the impact on pollution. But before we get there, I want to extend a very warm welcome to everyone who's joined us today. This session is being held virtually, as we know, coinciding with the high-level political forum. We feel that this session will be relevant and impactful and hopefully helpful for you as the HLPF is reviewing one of the SDGs that they're reviewing is SDG 6 on clean water and sanitation. Today, we'll be addressing marine debris and how to detect and measure the impact of marine debris on the health of the ocean and the preservation of the marine ecosystems. We have three renowned speakers with us today, and I'll be handing this over to them shortly. But just to introduce them briefly, we have Christopher Witt, who's the president of the IEEE Oceanic Engineering Society. We have Renee Garello, professor emeritus of IMT Antarctique. And we have Dr. Christopher Wadman, chair of the IEEE Ocean Engineering Society Standing Committee on Standards. So without further ado, I will hand it over to Christopher. And I think, Christopher, you might want to touch upon, I guess if there's any questions along the way to use the chat or raise hand feature as well. But with that, the floor is yours, Christopher.
Thank you very much, Karen, and thank you everybody for joining us. Looking forward to talking a bit today about how the ocean is important for sustainability. As Karen mentioned, please feel free to use the chat function or raise your hand. There will be a Q&A time at the end after our speakers have their opportunity to present. So next slide, please. We're going to start with a little bit of setting the stage from me, and then Renee will speak on a guide to marine debris observation, and Christophe will then cover a little bit about standards related to marine litter. And then I'll recap with a few recommendations and outcomes, and then save some time for question and answers. Next slide. Keep going. Thank you. First of all, I hope it goes without saying, but perhaps it needs to be repeated, that the ocean is critically important to the planet. To sustainability, yes, but to the planet as a whole. Secretary General Antonio Guterres says the ocean plays a crucial role in the achievement of the Sustainable Development Goals and the livelihoods of billions of people. We urgently need to change how we interact with it. Next slide. Why is the ocean vitally important? Well, we need to better understand the ocean in order to better manage the ocean and to sustainably benefit from its ecosystem services and benefits. It's nearly impossible for us to meet the Sustainable Development Goals without a healthy ocean. The ocean provides livelihoods for millions of people. Marine phytoplankton account for nearly half of the world's oxygen production and nitrogen fixation. The deep ocean is well over 90% of the long-term carbon storage on the planet. Ocean ecosystems provide coastal and storm protection, as well as opportunities for recreation and tourism. Seafood is essential for food security. Historically, about 1/3 of hydrocarbon production was offshore, and in the future, we could expect a similar proportion of renewable energy to be produced offshore. An OECD report from 2016 suggested that in the period from 2016 to 2030, the ocean economy could double to a value of more than $3 trillion with approximately 40 million full-time jobs. Next slide. What is our impact on the ocean? Of course, today we're going to focus on marine debris, marine litter, but in general, it is a fallacy to think that the ocean is so big that humanity's impact is not noticeable. The ocean is actually acting as our biggest climate buffer. About 30% of all CO2 emissions to date have been absorbed into the ocean, and that's what's driving acidification and sea level rise, deoxygenation, coral bleaching events, extreme weather, storm formation. Over 90% of the excess heat energy from the last 100 years of climate change has been stored in the deep ocean. There's some really staggering statistics there, but I won't take the time today to get into it. But today we're going to talk a bit more specifically about pollution, and the impact of pollution is also pervasive and easily seen. There's the loss of biodiversity, but there's also health impacts and impacts to the food security and food chain. Next slide. Who is affected by our impact on the ocean? The short answer is everyone. More than 600 million people live in coastal regions that are less than 10 meters above sea level. Nearly a third of the population of the planet lives within 100 kilometers of a coastline. And those areas tend to experience higher than average rates of growth and urbanization. On about 3 billion people get 20% of their animal protein from ocean sources, and in some developing countries, that number is more than 50%. Most goods and services are transported by sea in some way. And of course, the things I've already mentioned, like loss of biodiversity, extreme weather, storm hazards, sea level rise, impacts on food security, energy security, and other ecosystem services, those don't know any borders. Next slide, please. What is the knowledge gap that we face in order to better manage and benefit from the ocean's services? It's perhaps not as widely appreciated as it could be how hard it is to do science and to monitor the ocean in order to inform good policy and good management. It's probably obvious that there are physical challenges of the extremely harsh environment, corrosion, storms, surface action, waves, but even more challenging than the physical environment are the fundamental limitations. These are physics limitations. The ocean is a black box to us. Most of the traditional sensing methods don't work in water because water is generally opaque to most electromagnetic waves. So there's no such thing as GPS underwater. No radio, no Wi-Fi, satellite imaging can only penetrate in the first few meters of the surface of the ocean, leaving the vast volume of the ocean and where all of the resources are and all the physical and chemical and biological processes occur is largely unobserved. You could imagine like looking into a room, a dark room with a straw, like looking through a straw into a dark room. We send out a ship, we do one measurement, we have a fixed observation point, we get one measurement. But it is completely different from any other domain that we routinely study. Sound bites that we often hear about, we know more about the surface of the moon or the surface of Mars than we do about the ocean. Those are based on that reality of the difficulties of monitoring and measuring inside the ocean. I mean, they're specifically referring to sea bottom bathymetry, but the same thing applies to lots of other necessary data. There's one other factor, and that is for large areas of the globe, there's a lack of effective and adequate long-term monitoring, protection, regulation, and governance. And of course, there's a huge amount of the ocean that is beyond national jurisdiction. The BBNJ, the Law of the Sea Treaty, is a huge first step, but it's just the first step, and there's so much more needed to coordinate efforts across technology areas and across policy domains to enable that necessary monitoring, management, and social benefit from the resources of the ocean. And on that note, I'm going to turn it over to Renee to talk about marine debris.
Okay, unmute is better. Good morning, good evening, good day to everyone, wherever you are. So I'm René Guerrero. I'm a professor at IMT Atlantic. As was said before, IMT Atlantic is a very large engineering school in France, in my city in Brest. And the title is in French. There is still the accent on the debris, the E of debris. Anyway, and I'm an IEEE Life Fellow, meaning that I'm old enough to be a fellow. And okay, so next slide, please. I am also a former IEEE OES president. So that is what I presented in my time 10 years ago, OES in the IEEE. So you see on the left-hand side, the part which is dedicated to, that is what we do into IEEE, dedicated to the sensors and the vehicles in order to gather, to observe, eventually, possibly, monitor and gather data. And the data are processed, which is then on the right-hand side of the slide, and in order to get information. And finally, global observation, global, let's say, modeling or models of the environment and of the ocean. That is exactly what is OES, and that is what I will apply for marine debris and marine litter. So next slide, please. We do science and we do technology. For me, it's the same. Science and technology are both talking together. This is a very nice picture that I borrowed many years ago at a conference we had in Yeosu in Korea, Oceans Conference. And because it depicts exactly what we do, we observe the ocean from the bottom to the surface and from below and from above and below. So you see that the red dots are the multi-sources observation and the way that are gathered and sent to data centers through communication links. And so this is a data and the communication code we know, like when you call with a cell phone. And there is all the underwater stuff, which are through devices, through sensors, through vehicles, which are either at the bottom. It's more difficult, of course, because the bottom is it's not the ocean is quite deep, or in between, or buoys that goes up and down, or at the surface. So there are many sources of observation, and that is part of the difficulty. So next slide, please. Okay, in terms really of marine litter, marine debris, that is mainly plastic, let's say, call it plastic. Relevant data are from the coastline and the sources of, that is the rivers and the river mouth and the coastline and the sea surface, and then everything below. And the plastic goes at, of course, the surface through the rivers, but then started to fragment, as it is written here, a very nice paper, by the way, and biodegrade, as it is written. But in the meantime, before it is biodegraded and sent back to the seafloor, you have a lot of ingestion by all the animals in the ocean, and also by all the life in the ocean, including the algae and so on, and plankton. And so plastic, even though, and I will come back to that later, the density is not very high, then it's enough. 15 million tons per year is enough to go everywhere. So sources of the plastics in the ocean, and that's the object and the subject of the next slide, please. Is bring challenges for observation. If you recall, I said that on the left-hand side of my first slide, I was talking about the way to observe. So we know that 90% of the plastic flows in the ocean from the rivers. And so there is already a possibility to measure directly the concentration via in situ samples at the water surface. It's not enough, of course. we need to know also the motion and to measure the movement or motion through what we basically the community call remote sensing. Any device that can see beyond the end of your arm is remote sensing. So there is, of course, in situ observation, the drones, the field survey, the indirect indicators, that is what the collection of plastics on the beaches, the ship traffic, etc., etc. So there are a lot of ways to do this measurement, but it is static, and you have to add the ocean circulation. The ocean is not it's a body which is fluid and is moving, and so there is circulation on the ocean, and so everything that goes there at the river mouth, for instance, and somewhere in the world, you know. So, for instance, the east coast of Northern America or Canada, a plastic device takes about that's a few weeks, 2 months to go to my place in Europe, in Brittany, in France. So it's and that's I will show a picture of this kind of problem. So one way that is still potential is using satellites. Of course, we have zillions. No, maybe I'm exaggerating. Lots and lots of satellites in space, and the interest is that they cover a very large area. So the space they cover is very interesting. The time, of course, resolution, they rotate around the Earth, so they are not here just to look at the same place. If not, they fall, or they are very deep in space, and so that's the resolution is very poor. So these are challenges, and we are scientists, so we love challenges because we are the champion to go over. So next slide, please. Okay, this is a picture that I took somewhere, I don't remember where, but showing some, not all, the parameters that we can get from space using satellites. So we can have the temperature of the surface. As Christopher was saying, the satellites don't see very deep. You know, it's a few, as he said, if it is radar, it's a few millimeters or few centimeters. And for the rest, it's the skin of the ocean. But we can see the temperature, the color. We can see the sea level anomaly, which are linked to altimetry. We can have altimetry and temperature talking together, and then we can get some ideas of currents. We can see with radars, we can see many other parameters like wind, waves, currents, and stuff like that. So there are, again, within the community of the satellites, people, there are already lots of parameters to add to the in situ one. So next slide, please, in order to take that into account. We need also to add, because I said when you get an information from a satellite or in situ, it's kind of static. You get information at a given time and on a given area, and it's static. So you need to know the motion and the dispersion at the ocean surface. And for that, our colleague doing physical oceanography, they have developed models. You see on the left-hand side on the top, a model that look for 20 or 30 years, and that this one stopped at the year 2013, because that was when the paper was written, I think. And then using these models, which are numerical, they can predict where there will be an accumulation of particles. They work about particles, but the plastics, in a sense, even the bottom is kind of a big particle. So it goes to this accumulation, which are either eddies or gyros, gyre in French. And then we have to go and see if the in situ observation confirm that model. And the latest over the last 10 years, we have had enough information and models that had enough resolution to assess that we have a fairly good idea where the accumulation are, which is important, because if you want to collect plastic you have to know where the plastic is, and it is not exactly at the surface, it's in between, a bit below. And then, of course, as I said, by degradation going down. So, and the density is not very high. So that's another source. So we have many sources, the in situ, the satellites, the modules, which is a source by itself. And next slide, please. Maybe, okay. Where I wanted to show some kind of underwater in situ measurements. Christoph Wallman has worked on some of equivalent topics. And these are European projects. That's why I put that on this in the slide. So there are ways of going, sending instruments, vehicles to capture through a large volume capture samples, and then to go on board a ship or somewhere else and to process the samples. So there are many ways to do something that is going a bit around the static observation, because the vehicles here is moving and then collecting along a long, normally a quite long path. So next slide, please. Okay. Yeah, this one is the next slide. So again, this raises again more challenges. So first, the first one is, how do we observe? And we were asked by UNEP, the UN Environmental Program, a few years ago, to gather several, 20 maybe, science and technology people like me. And in order, and the title is explicit, to propose a global data and information platform for monitoring the marine litter and inform action. The leader was one of my colleagues, Emily from NOAA. And then you go to the paper, and it's, so we write a white paper. So that's the basics, the observation, but also some kind of already possible solution, like gathering all the information onto a platform. Okay, you have to understand the platform is numerical, of course, digital, and then trying to from all the sources to get some really some observation, some information and observation that are going together. And the problem of that multi-sources is, how do we integrate all these sources? Because the diversity, as I presented in the previous slides, are above, below the surface, on the beach, the circulation models, the in situ, etc., etc. The communities are different, and even though we are in the same field, on the same boat, science, technology, citizen science, or oriented regionally or globally or by country, these diverse communities, they don't, sometimes they don't speak together. And we have also a diversity of data processing. So we have different platforms. What kind of post or pre-processing do we do? Do we process the data when we acquire the data? We do the observation when we acquire the data. Do we process afterwards, because the flow of data is so large from satellite? For instance, you have petabytes of data everywhere, probably per day. So it's doing it online is a bit difficult, etc. Do we calibrate first, or do we have less expensive devices, less calibrated, but a lot of them, and so at the end we have a good answer, a good set of data? Well, and then there is a management. So for the management, since the last, in my case anyway, last 10 years, we have started to look into, well, nowadays we call it artificial intelligence. Okay, it's another way of processing through methods that are deep learning or core deep learning or stuff like that. And the next slide show a bit of the idea about that role of AI. Yeah, so on the it's with my colleague from IFREMER, which is an institute in for the research in the ocean in France and in my city in Brest. And on the right hand side, you see the way that data are gathered by in situ platform, connected or mixed with satellite, which is on the right, assimilated a bit like they do it for the weather forecast. Also from, as I said that already, remote sensing, then there is kind of planning algorithm to make some decision and then go back to the platform. And on the left-hand side, you see the two theory, the data model loop. One is the modeling driven by the theory. So you have the scientist, the physicist comes with a theory, and then they make an hypothesis, and in the end they get observation, and the observation must fit the theory. I'm just kidding. Of the observations, they assess the theory. Or you gather all the data, and that's what we do, and from different sources, that's a modeling which is driven by the data. So there are observations, and then from the complete observation, you make hypotheses, and then you get a possible theory. Important part is hypothesis, and that's where the artificial intelligence comes, because using this algorithm, for me, artificial intelligence is an algorithm, you can go and get all the different parameters that are directly observed or hidden in some observations, put that together and provide hypotheses. So on the next slide, I have a good example. Okay, so you have two sharks, and the shark says, I let you understand what they mean. Ketchup, we follow the ketchup trail for 3 miles. So it means that they add lots of parameters. The sharks are artificial intelligence in a sense. And they add lots of parameters, and they put the parameters together, and they made an hypothesis. It's a red trail, so it's somewhere human there, and that means food. And problem, the hypothesis was wrong. So I also put the quote from Sherlock Holmes. When you have excluded the impossible, whatever remains, however improbable, must be the truth. So that is us human. So meaning, what do I mean by that? I mean that artificial intelligence give an answer, possibly or probably correct, but not sometimes not intelligent by itself. And so the human has to be there and say, yeah, well, maybe, but you're wrong. Okay, next slide, please. And I think, okay, I wanted to show some possibility of merging what I said before and come up with, in terms of application, what I call a sea cleaning guidance. So on the left-hand side, you see a map of floating marine debris along the Indonesian coast, and that comes from an atlas from my colleague at IRD, Christophe Maes. And based on the modeling that of the circulation, and based on observation, and providing a kind of with the atlas, kind of the most probable place where the plastic are. And on top of that, which I didn't represent on this slide, are all the information from satellites or from buoys, from drifting buoys and other in situ devices that can focus where the accumulation of plastic is. And then I put a picture on the right-hand side of a project which normally should be ready by 2025, which is a giant catamaran called a Manta project. And the aim is to, it's very large. This is an artist view, by the way. It's not yet built. And it's an NGO which is called Sea Cleaners. And the idea is through our guidance, they go where the plastic is floating or in between, and then gather the plastic and they do lots of transformation, recycling, whatever, or just collecting on board, and they go back. So next slide, please. And I think that would be the last one. Thank you then. And plastic is unfortunately here for a long time again. And we are not the last to be responsible for it. Thank you.
Can I continue?
I
Yes,
think it's your turn, Christoph.
All right, thank you. I thought there's some final word from someone else. All right, so thank you very much for inviting me to this interesting event. So I'm going to talk about standards in the implementation of marine litter monitoring and removal. And I'm chairing the Standing Committee on Standard of the IEEE OES, the Ocean Engineering Society. Next slide, please. So the text that you read here is taken from the webpage of the UN Environment Program. It has been mentioned by René Carello before, and actually I will allude to some of the themes that René brought up. And first of all, you see the definition. What is meant with marine litter is anything that's solid material that's disposed or abandoned marine and coastal environment. And the issue is that this marine litter has a very slow rate of degradation, and therefore, a lot of this material accumulates, in particular in the surface region, and that makes it a rather difficult issue. And you see here in red the amount of pieces of trash that you can find in the ocean, in particular at the surface. It's about 1,000 of pieces of trash, and that stays afloat on every square mile of ocean. And it's particular microplastic that causes the main headaches. Next slide, please. So the thing is, why is it such a huge issue? Everyone knows about that. Maybe 10 or 15 years, the discussion has been started. And everyone who goes to the beach also see these plastic bottles lying there from time to time. And it's everywhere. And it's not just at certain locations. And so it's just a matter of where they accumulate in the first place. So the issue is there are deficient implementation of regulation standards. That's our topic at IEEE OES standards. That improve the situation, a lack of awareness among main stakeholders and the general public, and this together makes the main issue, or produce a main issue, that the marine litter problem not only remains but continues to increase worldwide. And, particularly with these regulation standards, it's about standards of disposal of marine litter. I'm going to talk about in the next slide about standards how to monitor and remove these plastic. Okay, so there's a lot of research that have been carried out in all parts of the world. And there are some standards methodologies that have been identified, so to say, as a first step. And these are used for detection, identification of microplastics, so say, put it into separate categories. But there's actually a huge variety of methodologies has been developed as part of that. So I think René mentioned it already. Different communities are using different methodologies to observe and remove this material. And that's issue that you cannot really compare these data. They have different quality and resolution. Okay, next slide. That's why we need these standards. Okay, what we need to have is proper global estimation based on standardized approaches. And if we don't have it achieved, the standardization process, we have an issue in introducing efficient management and reduction measures. And that's probably very easy to understand. And why the next issue that we face is a joint international database, which would facilitate the collection of such data and improve standardization and comparability. And you know, that's this topic of joint international database. It's some sort of coordinated approach that is needed, and not that you say, okay, we already have data available in certain databases in certain part of the world. You have to integrate them, and that's one of the main issues. And again, this is an issue of standardization. In that case, it's standardization of data formats, the way how these data have collected. It's seen here as streamlining of data flows. That's what I'm talking about here. Okay, next slide, please. So as an intermediate summary of needs, it's clear that we need a standardized methodology to ensure comparability and consistency of collected data. And it's not just that we send out people say, you know, just do something, but I think it has to be a structured approach in a way that we have a technical management group identified, which has which comes up with some measures or some ideas how to standardize the methodology. And the next step, so on the next level, these ideas, concepts have to be implemented by this technical activity group. And I wanted to emphasize this because this is typical for standards to have a structured approach to that and not just say, okay, we have here an immediate issue that has to be solved, and then people are, you know, removing the plastic and say now everything is fine. So it's more than that. It's actually, you have to develop criteria, and which is seen here on the next bullet point, development criteria and methodology standards for good environmental status has to be developed. And within the European Union, a so-called Marine Strategy Framework Directive had been developed, which is crucial. And I know that in other countries, they are also looking at that. They're taking this as a template, and maybe this should be discussed on a global scale, but this is a good way to go ahead. And what I also mentioned is a joint international coordinated spatial data infrastructure has to be identified or built up. So it would be ideal if we can make use of existing spatial data infrastructures, but this is something that has to be explored. Okay, so next slide, please. Okay, so what's actually available as part of a process that can be applied? So I'm talking about a process-driven approach, and that is very typical for a method that I'm going to explain the next slide. What you see here on the right-hand side is a graph that is taken from the framework of ocean observing. This is developed by GOOSE, which is part of the IOC Intergovernmental Oceanographic Committee. And this is a very typical approach that you can see for so-called systems engineering concepts. You know, like in that case, they call it issues. I would call it requirements. And from these requirements, you derive your measurement needs, and you end up with essential variables, in this case, essential ocean variables. And those people who know that in other domains, a similar approach is used, they know about essential climate variables. So the ocean community is using a template that actually has been developed as part of the World Climate Research Program. And below that comes the actual observation systems, the deployment and maintenance, and then, with the data being collected, data product created, you identify a feedback loop. This is very typical for systems engineering approach, and this is something that I would like to suggest as a process-driven approach. Next slide. Okay, again, I emphasize this, and the system engineering methodology has been developed in the aerospace business and has been used or is in use by meteorological community, but not in the ocean community to that extent that it should be used, I think. And here is just the abstract model. It's actually called a V diagram. You see again on the left-hand side the system level requirements, then the design, you can also call it specifications, and then the implementation, design verification, and system verification. And between these two branches of the V diagram, there's a feedback loop actually there on each level, design verification level, and system level, system verification and feedback loop. That's very typical. And I think that's very important to have a good control on every step that you are doing. And this type of methodology is used whenever you have a very complex system. You have different parts of the world, different issues that you are facing, but you have to define an overarching goal and go from there to the implementation phase. Okay, so next slide, please. Just to show you to what degree this has been developed, there's actually a standard that has been developed and it has been updated in 2023. It's called the System Software Engineering System Lifetime Cycle Processes Standard. And it's a standard developed between ISO, IEC, and IEEE. This is, by the way, also very typical. It's not always that IEEE or ISO is develop their own standards, but they're looking for a coordinated approach. In particular, if you have topics that are so overarching, like the system engineering. And so I took out one of the graphs from the standard. On the right-hand side, you see this complexity that's behind that. And so it's also typical for standards that people are saying, I actually don't want to get involved into this so-called administrative stuff. I don't want to spend too much time on that. Instead, I would like to do some sort of real work. And that's what I think is a very typical attitude in ocean sciences. People say, okay, I have to document everything what I'm doing, but I actually want to do research. I want to come up with some new results. But in that case, if you want to collaborate on a global scale, I think you have to have some sort of coordination, and this could be a framework to work in. Next slide, please. Okay, so that's actually my final slide. So leave some time for discussions. I think it's pretty clear for everyone that we need standards for every step in the monitor and removal process. And these have to be developed. And so IEEE is ready to help in that. And that's why this event has been organized. Existing standards on structure, the management implementation should be applied. Again, this is you're building up on expertise, on knowledge that has been developed in the past, and that could help in this entire process. And, organizations with a high level of technical expertise like IEEE are ready to provide their support. And that's what I wanted to present today. And thank you very much for your attention. Looking forward to your questions.
Thank you, Christoph. So I'll just wrap up very briefly, and you can feel free to put a question in the chat right now if you have any. So we've learned a lot about the monitoring of marine debris, particularly plastics in the ocean, and about how standards can help. I think in a general sense, we understand that technology standards can drive down costs. And in the ocean technology sphere, we rely a lot on automated systems and sensors. So we want to see those things become more affordable and widespread. And that will enable better ocean science, more efficient transport, more affordable renewable energy, better food security. So the IEEE Oceanic Engineering Society is starting to work on some of the ideas that Christoph talked about. For example, we're drafting a recommended practice to provide a framework to address tracking, monitoring, and prevention of plastic pollution. But there's lots more needed. We need cooperation between policy and technology. I mentioned at the beginning the multiple various jurisdictions that are involved when you want to do large-scale scientific observations or other activities. The Law of the Sea Treaty is the first step, but just a first step. And technology, science, and policy and governance need to work together to enable better management and monitoring of the ocean. An example of how standards and policy can be complementary. Right now, the navigation operation of automated vehicles in the ocean is really not widely or consistently regulated. That mostly affects small science research platforms right now, and there's thousands of them out there. But very soon we're going to see many other sectors operating automated systems at sea, and coordinating the policy frameworks and the regulations will be really important. So follow-ups. The technology conferences that we participate in within IEEE as a whole and within the Oceanic Engineering Society as a part of IEEE include our Oceans Conference and Exhibition. We have that twice a year. This fall in a year from now. We are also participating with IEEE in side events like this one. There'll be another panel leading up to the General Assembly in September. We will have a presence at the International Oceanographic Commission's Ocean Decade Conference next April. And then we hope to have a presence at the Ocean Conference in France in 2025. But there's certainly more room for our communities to work together. So with that, we can probably open it up to some questions. You want to move to the next slide, Karen? While we're waiting for people to put questions in the chat, I thought I could ask both Christoph and Renee if they wanted to comment a little bit on what might be limitations or obstacles to hamper the standards development process for ocean technology specifically.
If I may start.
Yeah.
So I think what I mentioned in my presentation, a lot of people are already working in this field. So they come up with some ideas and they seem to work for them. And that's the issue then if you say someone else is saying we have a different approach. So this harmonization and coordination is a rather lengthy process that one has to go through. And so if organizations like United Nations would moderate this process, that would be very helpful. You know, all these different methodologies that are already available for removing plastic and monitoring plastic, this is a huge topic that one has to address. And that's, from my point of view, a major obstacle. Thank you.
If I may add also, a standard it's a description of a mechanism that allows to have some answers to the problem. And the main difficulty, I think, will be or is when the standard is seen as a directive. So that's why when we develop a standard, we have to include also the different approaches, except if they are completely, let's say, antagonists. but some of the methods won't work in some places. So that has to be taken into account.
Thank you both. So one question in the chat, are data planned to be made available using any dedicated IEEE cloud solutions? And do we have any collaborations with, for example, the US Environmental Protection Agency's EnvirAtlas? Renee, perhaps you can take that one.
Sure. Well, I'm not at that level of IEEE where I know about the if a cloud or not is possible, but it's completely within the possibilities IEEE has developed, not based on what we volunteers do, but they develop on itself some solutions. So it's in the same at the same level, I think, as the one at the European level. I'm involved with the European project, which started some years ago, which is now in the second phase, which is called Blue Cloud. And the new one is called Blue Cloud 26, meaning that the aim is to have a cloud in 2026 for anything related to blue, meaning the ocean, of course, related to the ocean. And of course, what we put in the cloud are data. So I don't know about IEEE. I don't know if the Karens, you have more info than I have, but it could be something that we could push at the level of the board in order to see if the IT and ITC guys and ladies, not only guys, could be interested in developing a cloud for not only their members, but for the complete community.
Karen
also-
McCabe, sorry, go ahead, Christoph.
May I add something to that? So again, I think the aim will be to use existing data infrastructures, and therefore I think that's although that might be a good idea to explore whether IEEE cloud-based solutions would be ideal. I think one will probably first talk to organizations like NOAA. They have a central data infrastructure and CEI. And this is, so to say, the counterpart to activities that we have in Europe, like EMODNet, and what René just mentioned, the European Open Science Cloud. I think that's what we are aiming for, and that's where we see our partners, so to say, on a global level. Thank you.
Thank you, Christoph. Karen McCabe, did you want to add anything to this before I bring another question up?
No, I mean, I think it's a great question. And we definitely will take that into the IEEE platform, cloud-based solutions, to see, you know, what could be done there. Our organization is quite large and we have a lot of data sets available through some offerings. So we'll definitely look into that. So thank you.
Thanks, Karen. Yeah, I think that Christoph had a very good point that there are some existing services that the ocean technology and ocean science community already use and would want to coordinate with, and we wouldn't want to duplicate that, although certainly IEEE does have cloud services for other things like research outputs and individual contributions. But in terms of global systematic data, like the EnvirAtlas is like an atlas, we'd want to cooperate with existing solutions wherever possible. Okay, perhaps another question. I'm wondering, Renee, you talked a fair bit about the different data sources, lots of different ways of observing. Is there, what's the rationale, or what's the method for combining those different data sources? How does that work?
Well, there are already some organizations. Christoph mentioned EMODNet, for instance, and the idea is to collect the data and, let's say, curate data in order for the data to be put in a space which we call a data lake. It's usually the metaphoric way of speaking in our world. But so in the data lake, the data are kind of ready to be processed. And so if they are, and that's the main one of the challenges is to propose to this to put in this data lake data which are enough clean, let's say, in order to be processed faster by something, let's say, I don't like this word, but artificial intelligence, that is machine learning and deep learning and algorithm to process the data. It's what we did, or what I did 30 years ago. We call it signal processing. But nowadays, there are a bit of self-learning from the algorithm, which is very interesting. And then process the data in order to on this platform to create either a new vision of the data. In Europe, we are very and there is a very large program called Digital Twins of the Oceans, and are different champions for that, and also within the European hierarchy, program is at the top. So then there are lots of projects, and Digital Twins of the Ocean is, in a sense, a way to. It's different from a cloud, of course, but it's to propose something that is completely digital view of the 3D ocean, and then you can navigate, in a sense, inside that and make your own experiments. So I've the two main parts to answer your question are first the methods to put the data together in order to have some kind of possibility to process them at different level, but with a kind of let's say the probability that they are good enough or in correct shape, and second have again the strategy at the level of observation and gathering the data, acquiring the data, some kind of standards in these devices anyway. So that's to go back to what Christophe was saying earlier. The community don't really use. It's always puzzling that are very little standards for whatever you do in the ocean compared to what we do on land. Like you cannot get your telephone, cell phone, or whatever without any kind of standards included in it, and on the communication. If there is no standard, it doesn't work. So it's different in the ocean.
We'll perhaps we have time for maybe one more question, and I'll ask both Christophe and Renee to give like a 1-minute closing thought here. But maybe I'll see if I can prompt you to follow up on what you were just speaking about, Renee, when you mentioned that something about the quality of each data point. And I know that traditionally ocean science has had such a high cost to make every observation. You have to send a ship out that costs tens of thousands of dollars per day. So there's a very strong emphasis on making really high quality measurements. But when you're talking about digital twins and building a model so you can do your own experiments in a computer, isn't it important to also have enough quantity of data to verify those models, to ground truth those models? And so what's the trade-off, the tension between accuracy and precision, and what role does standards play in that? So I don't know if both of you want to have a 1-minute closing on that topic.
Okay, I go first. Yeah, it's very interesting question. Accuracy and precision. Yeah. On the one hand, I know that my colleague scientists, oceanographer, and so on, they want to have a device that is calibrated and gives an answer, whatever it is, but they know that it's the answer normally correct. Now the device could be precise, but all the device focus onto something which could be biased. That is, it's not on target. It's very precise somewhere on the target, and it's very expensive. So I'm advocating for plenty of smart sensors. We call that smart sensors, low-cost sensors, gathering data. They are not as well calibrated. They are much less expensive. There are a humongous number of them. And so in the end, the idea is, again, if you look at the target, they don't focus somewhere precisely on the target. It's a bit scattered, but on the average, they are on target, they are in center. And I think that we should use this in the same way that it's used on land for whatever tweet and text or SMS and so on, where you get zillions of petabytes of data, and in the end, you have the answer.
Christoph, the last word to you.
Okay, thank you. Yes, that's a very good question, Christoph, in regard to local sensors. I think they will play an important role in the future, and it's because, you know, if you think about parameters like pH or oxygen, this is a very expensive system that you have to come up with, and calibration process is also very difficult. And therefore, I think that's the way to go, to use these low-cost sensors and have some intermediate checks in between. That's what people are doing today already in the meteorological domain, for instance. And there's also one aspect, I think, that has been not fully understood or used, is that under certain conditions in the ocean, you can do some sort of calibration, even if of this type of standards. So if you say there's a homogeneous water body that is, so to say, passing by, and then you're expecting that all sensors show the right data. So the very simple ideas that people have to look at, and I'm pretty sure that IEEE and the people who contribute to Oceans Conference will soon come up with good strategies on that. Thank you.
Well, thank you very much, Christoph. I think we're right at our time, so I don't know if Karen, one of you would like to close us out here.
I was just checking to see if there's any hands raised or anything in the comment section, but I think I don't see anything. I'll just look to Karen Mulberry to double check. With that, I really can't thank you enough, our presenters today, for providing great insights and information and thoughts regarding this such critical, important topic. Thank you for everyone who joined us today, and we just wish you all a good rest of your day or evening, and look forward to seeing everyone maybe hopefully in person or some virtual event as we lead up to the Science Summit in the UN General Assembly, and as we look to progress to the SDGs. Karen, over to you if you have any closing remarks.
Thank you very much. Yes, I'd just like to note for everyone that if you'd like a copy of the slide deck and the recording for this session, it will be posted on the website that I added it into the chat. Or if you're looking for something in particular, if you can send me an email, I can make sure that I can get a copy of the slide deck to you. My email address is k.mulberry@IEEE.org, and I can put that in the chat as well for everyone.
Thank you, everyone. Goodbye.
Thank you.
Goodbye.